Welcome back to algorithms. So in our last set of videos, we introduced the sorting algorithm Quicksort. Today we're gonna kind of refresh a little tiny bit on how Quicksort works. If you need a refresher on the details of it and the details of the partition function, do check out the link that I'll include up here. But for now, what we'll do is we'll do a basic refresher on the architecture of Quicksort. Think a little bit about what the merging or what the partitioning is doing, and then we'll analyze this. And we'll try to figure out how can we understand best and worst case complexity for an algorithm like Quicksort. All right, so the basic architecture of Quicksort goes like this. First, you take an array, ideally an unsorted array, and you partition the array into two pieces. So we partition array into two pieces. There's multiple ways of doing the partitioning, right? In our last set of videos, we looked at a method called the Hoare partition, and we showed that the Hoare partition has a linear time complexity, right? So the Hoare partition takes an array, and then in linear time takes all of the small things and puts them on the left, and all the big things and puts them on the right. Right? And then it tells the Quicksort algorithm where that split point is. And that's all the partition is doing. It's just taking small stuff and moving it this way, big stuff and moving it this way. Okay, so then the second step in Quicksort is you have these two pieces, and you know a fact about the two pieces. The piece on the left is the small piece on the right is the big piece. And so now you recursively call Quicksort on both pieces. Right? So now you Quicksort both parts. I'll call them parts so that it calls out the partition function. Both parts. And then 3, you keep quicksorting both parts, right, until you're down to trivially small arrays. And then you know something. You know that every place that you could partition the array satisfies the following. It satisfies the stuff that is on the left is smaller, and the stuff that's on the right is bigger. And so after quicksorting all the way down to trivial arrays, now we know that's true. We know that small stuff is left, big stuff is right, and that's true no matter which pair of elements I'm talking about, or no matter where I split the array. And so that means we're done. So then I'm just going to write done here, right? So if we're thinking about this in terms of the divide and conquer kind of architecture or methodology, we have step 1 is a split, step 2 is a recursive solve, and then step 3 is a combine. But in Quicksort, it's already combined, right? Quicksort is an in-place sorting algorithm, or at least it should be done in place. It's quite a space-efficient algorithm. And so that means at the end, once we've finished quicksorting everything, we have this fact that small stuff is left, large stuff is right everywhere, which means that we're done. We've completed the sorting. So now the question is, how do we analyze the complexity of this algorithm? How do we think about what a best case input or a worst case input looks like for this? And it turns out this is a little bit tricky for Quicksort, and it's not quite obvious up front. So what is a best or worst case input look like? So one thing we could do is we could say, well, this looks a little bit like the divide and conquer architecture. So maybe there's a way we can take this and figure out a way to create inputs that take this and put it into the divide and conquer recurrence relation. And then we can use the master theorem to solve it. So one question we have to ask is, does this actually fit in the divide and conquer framework? And the issue is this. Recall back to merge sort. In merge sort, in our first step, we had complete control over where we split the array. Right? In merge sort, we said split the array exactly in half and then go merge sort each half. And for divide and conquer to really work, to really be able to use the master theorem, we need our subproblems to have equal size, or at least to have, for a large input, to have equal size, right? In order to be able to define B. But the issue with Quicksort is that we're not guaranteed that our two parts have equal size, right? all we get to do is split it into two parts and kind of hope that they're roughly equal in size. And if they're not, then we just have to continue, right? And so let's think about, at least just for starters, let's think about what we would get, what kind of complexity we would get if we were able to partition the array into two pieces. And if it's not quite clear to you that we can't guarantee that we're partitioning into two pieces of equal size, hold that thought, right? And think about why that might be true. And then we'll show some very clear examples in a little bit about why we can't guarantee that we can partition into equal size pieces. So here's our sort of first question. What if it were possible to split the array exactly down the middle? So what if somehow we got lucky and every single time we called Quicksort, it chose a pivot that just happened to be right in the middle of the array. It happened to belong right in the middle of that subarray. So what if the partition always splits in half? What does that give us? Well, it gives us something that we can drop directly into the recurrence relation and then use the master theorem for. So what it says is that we are going to have a linear time overhead, and then it says we're going to have two equal size pieces that we recurse on, and then we're done, right? So T of n equals 2, right? There's our two recursive calls. This is the both piece here. 2 times T of n over 2. And that second 2, where we divide n by 2, that says we've just split it exactly in half. Right? So maybe it's useful to say both connects there, half connects there. And then we have some linear time overhead, theta of n. And then this is exactly in the form that the master theorem really likes the best, right? And this is also exactly something we've analyzed before with merge sort, right? This gives us T of n is n log n, big theta of n log n. Okay. So that's a good scenario. It turns out that's a good scenario. It actually might not be obvious to you at this stage. But what's a bad scenario, right? What happens if we don't manage to split exactly in half, right? What might that give us? Well, let's think a little bit about what the recursion looks like here. So suppose I have an array, 1, 2, 3, 4, 5, 6, 7, 8, and I manage to split it exactly in half every single time. Let's ask how deep this recursion has to go. Well, if I split it exactly in half, then in the second level of recursion, I've got two arrays of size 4. And then in my third level of recursion, I've got 4 arrays of size 2. And then in the last level, I have 8 arrays of size 1. Okay. And so the question is, how many levels of recursion do we have to go through? Right? How deep does our call stack get? And it turns out it gets 3 deep. Right? So there's three levels here. So now let's think about what would have happened. And by the way, 3. I mean, this is a fundamental fact. 3 is the log base 2 of 8, right? So this is precisely a true fact, right? So if we have an input of size 8 and we happen to split in half every single time, then we'll get exactly log 8 levels. Okay, we'll recurse log 8 times. And each time we recurse, we have this linear overhead, and so then that's the thing we have to end up paying attention to. And so really what we want to do, like the goal here, is to minimize the number of times we recurse, because that minimizes the amount of overhead we have to put in overall. Okay. All right. So suppose we had a different scenario, and we'll show inputs in the next video about actually what could generate this scenario. But suppose we had a different scenario, and rather than splitting exactly in half, we went to kind of the opposite extreme, and we only split the very first element. Right? So what would happen if we only split the very first element every time? Well, the recursion tree would look quite different. So here's our 1, 2, 3, 4, 5, 6, 7, 8. There's our 8-element array. So suppose in our first recursion it split into a trivial array and into a length 7 array. 2, 3, 4, 5, 6, 7. Okay. You know, we shrunk the problem, so we're making progress. But, you know, I guess the question remains, are we making enough progress? And so then on our next recursion, this one's done. We don't, if we ever have a trivial array, we know it's in the right place, so we leave it. So that one's done. And then in our second recursion, suppose again we split into this trivial array and a length 6 array, right? So what we're going to essentially trace here is what would happen if every time we recurse, we just shrink the size of the array by 1. Well, you know, you can see already the triangle shape. You know, you'd end up with this triangle shape, and the question is, how deep would this recursion be? Well, it would be 7 levels deep, right? So here we've got 1, 2, all the way down to 7 before we get to a trivial array. Okay, and so what's 7? Well, 7 is 8 minus 1, and that turns out to also be fundamental, right? This triangle must have the same number of rows as it does columns for it to be well posed this way. And so this is now a tricky scenario. So this is 7 levels of recursion, and 7 here equals 8 minus 1, right? The size of the array minus 1 is the kind of recursion that we would see if we split off only the first element every single time. If we got incredibly unlucky and essentially, you know, picked the very worst pivot every single time, then we get this very deep recursion. So what's wrong with deep recursion? Well, again, at every single level of recursion, we have a linear operation that we're doing, right? We have this Hoare partition which has to look at every single one of the elements every single time. So the goal here really needs to be to shorten this recursion tree as much as possible, and to keep it as shallow as possible. And we'll think a little bit about, you know, in the next couple videos, we'll think a little bit about what kind of inputs could give us this. But the issue is, if we have a situation like this, we're stuck in the scenario where we have an n squared complexity. And so why is the complexity of this operation, why is the complexity of this particular run of the algorithm n squared? Well, it's because it's a triangle, right? Triangles are always n squared if they have the same number of rows as columns. And so essentially what we have is, here we've got an order n operation. Here we've got an order, I'm going to be a little bit casual here, and I'll say an order n minus 1 operation. Here we've got an order n minus 2 operation. And so this is, and then all the way down, how many of these are there? Well, there's n levels here. There's approximately n levels. So overall, there are n times n operations for an n squared overall time complexity. Okay. And it's not too hard to realize that this is actually the worst that you could get, right? The worst complexity class that you could achieve with Quicksort is the one that is an input that makes your recursion tree as deep as possible. And this is it. Okay. So now in the next video, we'll actually look at a couple inputs and think about what kinds of inputs could generate this worst case performance.